That's enough to get you going, isn't it?
Yes, thank you so much for inviting me. And feel free to interrupt me anytime. So, a little bit of me and my story. I've been at DePaul for about 15 years. I moved to the United States and Chicago in 2001. Before that, I was doing a postdoc at the University of Warwick after the University of Perugia PhD. And so as your professor told you, then I started with a PhD in statistics. And then when I was at University of Warwick in England, I started working on a project that involved Bayesian networks, which is a machine learning technique that is used for classification. And so that kind of took me to a completely different direction from a very mathematical PhD research to a much more applied and so it's still using very complicated math algorithms, but I could see some interesting application in a much bigger dimension, which a lot more features, a lot more variables than what I used to work with during my PhD. So kind of like, that's how I fell into machine learning and the data science world, which is what we call it nowadays, right? So what I'm going to talk to you about, I'm also I'm one of the faculty leaders for the graduate program in Predictive Analytics, which is a similar graduate program that you guys have over here, which is in machine learning and data science. So what I will be presenting today is a project that I worked with some students of our graduate program. So our graduate program has a requirement, a practical requirement, where students have to work on real-world data. And often we get requests from local organizations or companies that have projects that can be used as a capstone within our school, either in a course or outside, which is what we did. It was a project led by a faculty member, and Jen and David were the primary students leading this work. As you can see, the goal of the study was to develop this segmentation, which is a machine learning application to define similarities among objects or observations in our data sets. And so the data is related to the housing market and to the socioeconomic characteristics of northern Illinois around Chicago. So is any of you from Chicago or around Chicago? One person, two, three. Okay, so maybe you recognize where you live. So this study was funded by a grant of the Chicago Metropolitan Agency for Planning, and that's a regional planning organization, and their role is to support the policymakers in northeastern Illinois. And so they developed plans so their goal is to support and provide resources for these policymakers or local organizations as they develop new policies or new programs for the future. So they have to be ready if there are changes in the population, if there is an influx of young families to their communities in the next 10 years. They need to make sure that there will be houses that will be ready for these new families. There will be schools for those families. So really understanding the needs of the communities is important. So what we did was developing this model that gave this organization a tool to better understand the similarities among the different communities. That's the overall goal of the study. So let's see, let's change. So here is the overview. So 5:30, I should be done by 6:15 or so. So we're going to talk about the data that we used. Some of them are public data, some of them are private data. We're going to talk about 3 clustering approaches that we also used. I know many of you don't really have a background in data science or machine learning, so I'll just give you kind of like an understanding of what these techniques are without going into the details, more like an intuition. And then I'll show you the comparison of these techniques, and I'll show you what we did and the results through maps. And finally, I'll show you a tiny bit of this interactive data visualization tool that we developed that we're still developing. It's totally work in progress, very buggy, but I just want to give you a sense of what we did as a second phase of the project. So, the motivation. So, again, as I said before, we wanted to build this integrated model that explains the different characteristics of the communities around Chicago. So it's Cook County and a bunch of other counties. So we looked at 7 different counties in northern Illinois. And so if you understand this, the property or the market level characteristics of these communities, you can decide which policies might work better for certain communities. You can also talk to other mayors that have similar programs that you have, and so kind of develop a better and more integrated planning for the future. So that's the idea, right? And so also for, and at the end you can see that there is, with the housing market recovering, but not all communities are recovering at the same pace. We actually have communities that are still suffering. And so how do you handle that? How do you tell the policymakers that, that you need to support them, you need to provide some more help, okay? So that's something that we also discovered through this study. Here is the area or the region that we analyzed. So again, for the Chicago, the students that are from that area, you might recognize your county. We used public data from the census. So we used the 2000 census data and the 2013 American Community Survey, which is the way data are collected nowadays. There is no more complete population of the census is not going to send you these big questionnaires anymore. It's too expensive, so they sample. They select a group of the population and they collect data from them. And then we also use private data, and that's from our Institute for Housing Studies, which is a research institute at DePaul that has a clearinghouse and collect housing data, mortgage activities, and these are all private data, so that's their role. Region is subdivided into census tracts, so our data units are census tracts. Do you guys know what a census tract is? I didn't. So a census tract is this region in which, so the census divides the regions into these subdivisions. And in Chicago, typically a census tract is as big as a couple of blocks. And the data that are recorded through the census are at that level, because you can't record individual data, because that would be too sensitive, right? So they provide estimates at like 2 blocks type of region or unit. If you live out in the suburbs, the tract is bigger, as a wider area, just because a tract is based on the number of people inside. So they tend to divide or subdivide the regions into tracts, and the tracts tend to contain about 4,000 people. Again, there is a little bit of variation. So if you go out in the suburbs, as you would expect, the population is not as dense, so there would be like a bigger area, right? So in total, we have about 2,000 units or subdivisions of all these regions. And we removed all the regions, all the units that had no population. So you will see in the maps some gray areas, because those are the airports. So you have O'Hare, Midway, we have some industrial areas that have no people in it. So not of our interest. So I'm going to give you, I'm going to go really fast about this list of data, because who cares? So just to give you the different dimensions that we analyze in our study. This is, so you got a sense of, we got home values, we got values, demographic, education level, the age, the income level, and this is all census data. We also have housing characteristics, the size of the house, the number of people in each house, the age, the residential activity, the number of owners versus renters. We also used distressed sales, so the number of foreclosures, the number of cash sales. Cash sales is typically an indicator of distressed sale, low income, low value, okay? Any questions so far? So this is, again, some of this is a mixture of census and private data. And then we also included these change variables. We wanted to see also how communities have changed from the past. So we used the 2000 census data, and we looked at changes in terms of number of, whether shifts in the population. We looked at changing unemployment rates, income, number of children. So see whether communities have changed in terms of, becoming maybe with more older people versus younger families. So kind of get that sense of the dynamics, right? The dynamics within the different communities. So this data, you think, oh gosh, I have census data. They're going to be super clean, right? Easy to use. They're not. So there are quite a few challenges when you use census data. And I guess if you're a social scientist that use census data all the time, you know that. I did not know that I was going to spend about, 2 or 3 months just cleaning the data, which is the fun of data science. You probably, if you take a data science class, you know that you're going to spend 80% of your time cleaning the data and 20% modeling and having, developing these beautiful results. So that's where computer science plays a big role in data science when you do the data cleaning. So first of all, the census tracts are not fixed. They change over time. Because remember, the census tracts are defined based on the number of people. So because of shifts of population, there may be, especially in the urban communities like Chicago, you might have areas that in 2010, a certain number of people, and then a lot more people moved in, and new houses. So think about the Loop in Chicago. You got a lot of new development. So you got a lot more people in there. So the tracts had to be split. So you have new tracts created, different tracts, redesigned everywhere. So in order for us to compare 2013 with 2010, we had to map. And this is a computer science, a math program. So we had to create a mapping between the old tracts and the new tracts. So we did that. With the American Community Survey, we have an error with the sampling error. Because the American Community Survey, are you guys familiar with that? So they sent out surveys to, I think, 250,000 people every month throughout the United States. So every year, they sample about 3 million people, right? So that's about 2.5% of the entire population. So every time, so when you get data for a certain tract, so let's say income level, they didn't sample the entire population in that sample tract, in that census tract. They only took 2.5% of the people, or 3% of the people in there, right? So we have a problem with the margin of error of those sample estimates. So what we did is considering only values that were trustworthy, that gave us enough information, so where the margin of error wasn't too big. So sometimes if you have a very large margin of error and you're looking at an account, the actual interval could be any value between 0 and, let's say, 10, right? But 0 is in there, so how do you trust that value? It could be any value in that big range. So the typical approach is to compute this coefficient of variation and use a sample estimate only that has a coefficient of variation below 30%. So again, this is another issue that we had to deal with, and there were variables or features that were important and that we wanted to keep in the study. We had to do some data manipulation and aggregate the different levels together in order to get a sample estimate that was meaningful and usable. Okay, so this is our data preparation. And obviously you remove all the missing values, the outliers, you do the standardization, you do the usual steps for data preparation. So once we had all our features clean and ready to go, and you saw the list before, the idea now is to develop a clustering application. So what is clustering? So clustering is this machine learning methodology that we use to separate observations into groups. Each group contains similar observations, right? and then observations that are placed into separate groups are assumed to be different or have different features, different characteristics. And so there is this technique, and it's we call it unsupervised machine learning. It's an unsupervised algorithm because the problem is that we don't know what the actual number of groups is, right? So we're trying to discover the pattern among the data without knowing what the pattern is. So that's the unsupervised. So we will show you as I progress through this talk that there are different ways of selecting the right number of groups. There are objective metrics, and there are also subjective ways. And two needs to be combined in order to reach to that final results that you can use in practice. So there are, this is a mathematical approach. So we look at similarity between points using Euclidean distance. This is all numerical attributes, all numerical features, so I can just apply a typical distance metric between multidimensional points, and that's the simple Euclidean distance that we all know quite well. The quality of a clustering result is based on the separation among the groups. So a good clustering result will have dense clusters, so groups where the points are as close as possible to each other, means that they're similar, and separated groups means that each group should be far, right? So the optimal clustering result will have groups that are far from each other and points within each group that are pretty close to each other. And here is the evaluation methods for clustering results. So we call it cohesion. Cohesion is our quality in terms of the density within a cluster. So we measure cohesion, for instance, using within cluster sum of squares. If you did ANOVA in a statistical class, you probably have seen that. So we look at the distance between points in the cluster and then just take the average. That's one measure. That's cohesion, right? So we want that measure to be small. And then the other measure is separation. And the separation, you want the clusters to be separated, right? So you want points that belong to two different clusters to be as far as possible from each other. So you compute the inter distance, so the between cluster sum of squares. Again, the distance between different points. So we have different ways of measuring this, right? So when we run clustering algorithms, when we get to a final results, we check, am I getting enough separation? Are these clusters cohesive? Are they dense, right? Do they make sense? Okay, so the students worked on 3 different methodologies. One is the standard k-method, which is probably one of the most used techniques in clustering, together with k-means. It's very effective. It's also easy to explain. And this is an important issue when you work with a client, right? Because you need to be able to explain what you did. And if you manage to use a technique that is powerful, but is also easy to understand, the business audience or the client will believe and trust your study a lot better, right? And k-methods is very intuitive, and it's also very effective, which is obviously the main point, right? So then we use 2 other techniques that are more complicated, computationally intensive, more interesting from a machine learning perspective. One is the self-organizing maps, which is related to artificial neural networks. And the other one is spectral density clustering, which is a newer technique that was developed in 2001. It's really cool. And so from a student's perspective, you kind of learn some new technique that's really neat math underneath. So k-methods, it's purely algorithmic. It's a partitioning technique, which means that it defines separate groups of observations. So for the computer scientists here, you probably can read the algorithm pretty easily. One of the issues that we have is that when we apply clustering, we need to define the number of groups. So often we apply clustering multiple times. So because you don't know, right? I told you before, it's an unsupervised technique. I don't know how many groups I should find, right, among these observations. Think about clustering is used in market segmentation, like, you know, think about a customer analytics applications where companies group customers that have similar behavior, right, in terms of what they buy at the store. And you don't know how many groups you have, right, how many types of customers you have. So, and that's the goal of your algorithm, is to discover that. So what we do is select different Ks and run the clustering methods multiple times, and then compare the results and select the best that we get. The best is defined in different ways. So we use the metric that we use in here is Euclidean. It really depends on the features of your data. There are a lot of different metrics that you can use depending on the features of your data. If you have categorical data, you cannot use Euclidean, so you will use a different metric. So all these different techniques that are part of this algorithm. So you set these initial centers of the, so think about this as an iterative process. You select, let's say, we start with, I want to discover 5 groups. You select 5 values in your data set, totally at random, and the algorithm will group points to 5 different groups based on the distance from these initial points. So each point is assigned to the cluster with the closest centroid. And then once you have divided up all the points, the algorithm checks within each cluster and recreate and recompute the center of the cluster, and then reshuffle the points again. So at the end, the algorithm will converge when there are no more points that travel around. So when the clusters that are formed are stable and there is no more change. And at that point, your clustering is done. So that's K-methods. As I said, pretty easy to understand, easy to explain, right? Well, then we have the Goldilocks problem. I say, what is K? How many values should I select? If it's too large, if I take a K that, let's say it's too small, right? I take, let's say there are 10 groups, but I only decide to look for 2 groups, what happens? Your groups are too big, right? You end up with these very large groups and really not really telling you much about the characteristics. So that's too coarse. If you take a K that is too large, if you create too many subgroups, then you just, it's just too small. It's hard to differentiate among the different clusters. It's kind of like leading to overfitting. So that's not good. So the idea is to find the just right K. Okay, how do we do that? Well, there are different ways. We can use these empirical metrics, which is silhouette and gap statistic. And these are based on measurements of the data. And then we also use domain knowledge. And the domain knowledge here and interpretation of the results is a key factor when you apply clustering. Just using standard objective metrics by themselves is not sufficient. Because again, this is a technique that you have to use to learn about the data, right? So you're trying to discover. And so making sure that the clusters that you create make sense is one of the most important part of clustering. And here are some of the references for both of those techniques. So I'm checking the time to see. So I have a few slides that explain some of these statistics. The gap statistic is really cool. It's being developed in 2001 by a group of researchers at Stanford. And so they look at this, so this gap statistic, it's kind of, the idea behind is that, so the idea is that we assume that your data, there is a true number of groups that you want to discover. So your distribution, your data distribution, So it's kind of, so from a statistical perspective, there is a mixture of distributions, and you know that there's a fixed k, right? And the number k is what you want to identify. There's a true k that you want to find, okay? And the point of this gap statistic is that the assumption is that so you have this optimal k that you want to find. So if you define a number of groups that is below this optimal k, then the changes in the dispersion metric, in this metric of the cohesion of the clusters, so as you get closer and closer to the optimal value of k, your dispersion matrix decreases at a much higher rate, okay? So it means that you're improving, right? You're improving your clustering result at a much faster pace once you get close to the optimal k. But if you pass the optimal k, and let's say my optimal k is 5, and I start building clusters, and I started with 2 clusters and 3 clusters, you can say I'm improving, right? I'm getting closer and closer to the true value of 5. And this metric that I use to evaluate quality will get better and better at much faster pace. But once I jump and I say, okay, now I pass 5, and I say, okay, I'm going to start creating 6 or 7 clusters, the improvement on that statistic will get smaller and smaller. And so the gap statistic is a way of measuring this different degree of changes. And the idea is that the best k, the best number of groups, can be found when this gap statistic is at the maximum value. And that's the idea behind. So I'm going to skip the actual details, and you guys, I can leave the slides here. There is a reference to the paper, so feel free to go and evaluate. The silhouette coefficient is a coefficient that is a coefficient that, so the formula there, what this formula is, BI measures the dispersion. So that's the separation. This is the cohesion, so that's the density within the cluster. So this is sort of a joint metric of separation and cohesion. And the SI, so we compute that for each point. The average silhouette is a global measure of the quality of your clusters. And we want this measure to be as close as possible to 1. But 1 is our ideal world, we never get there. It's usually anything that is positive, above 0 is, you get a decent result. So this is what happens in our data. So what you can see, the silhouette, what we look for is knees, right? So this type of, how do you call those? Like knee, that's how we call it. So it kind of changes, right? So you get a fast decrease, and then it stops decreasing. So the decrease, or the extent of the decrease changes, the slope changes. So as you can see here, either 7, so this is the results for our study. So let me explain this graph here. So here is the silhouette web. This is the results of the silhouette for different Ks. So here we create a clustering with 2 groups, 3 groups, 4 groups, and so on, right? Is that clear? Okay, so the idea here, okay, so when you observe some type of change in the slope, that's where we say, okay, so that's a good K. So here it could be either 7 or 8. Now we chose 8 because when we compare the results, 8 made more sense to us. It defined a certain grouping of the data that was helpful, was meaningful, and that's why we kept 8. Similar for the gap statistic. Here we said, okay, when the gap is the highest, that should be a good value. So really here it could be 6, 7, so 6 would have been a good point, a good result too, right? I could have just said, okay, let's do 6 groups. However, with 6 groups, we were missing some groupings that revealed to be quite important from a practical application. So we ended up to say, okay, so 8 seemed to be a good value, okay? So again, remember that compromise between the objective metrics, which are the silhouette and the gap statistic, and the actual makes sense use of the techniques. So that's where we are. So we use those different techniques, the k-medoids, then we use the self-organizing maps. So these are, so self-organizing maps are a technique that was developed in the 80s. So with k-medoids, it's just this really neat technique that, you start with different points and then you group and partition data. With self-organizing maps, it's more complicated to explain, and it's obviously it's more intensive computationally. And the idea is that you create a projection. So you start with your the space of your data with a k-dimensional space. In our case, we had about, I don't know, 50 or 60 variables or something. So you have like a 60-dimensional space, and you project it onto a 2-dimensional space, which is this topological map that we call. And this 2-dimensional space allows us to, first of all, visualize the data, right? So this technique was developed as a way of visualizing high-dimensional data, because this is one of the actually challenges in data science, is like how do you visualize when data that are defined with so many attributes. And by visualizing in a smaller 2-dimensional space, you can actually see the similarities among the observations. So, so this is the dual application of self-organizing maps. They tend to be quite helpful, and we use them because this technique was used in a similar urban study. I think it was Baltimore, and it was successful for their study. So I was like, well, let's give it a try, right, and see if it works for us as well. Well, it didn't work that well. Here's some of the overview, which I'm gonna kind of skip because I think I'm running out of time. And then we have spectral clustering. Spectral clustering is a newer technique. It's more powerful than any other technique that I've showed you. So k-medoids and the self-organizing maps are good to discover groups that are elliptical. So it's kind of like irregular shaped groups. So so groups that are easier to detect. K-medoids, self-organizing maps do a good job. If you have harder, more complex situations where the groups are not elliptical, they might be like crisscrossing each other, the spectral clustering has proven to be much more effective. And the idea of spectral clustering is related to graph theory. So again, it's math and computer science here applied. So where points are, so your object space, your data values, your matrix of points are represented through a graph. So again, it's quite intuitive if you think about it. So just to give you an idea, so this is a simple graph. Each vertex is a point, and then the points are connected if according to some distance metric, right? So similar to the k-medoids idea. So if 2 points are somewhat close to each other, we connect them with an edge. And so there are different ways in which we build the graphs. One way is to, again, give a constraint on the distance between points. And you can say, okay, so if this distance is below a certain constant c, we connect the 2 points. So you end up with a graph, right? Other ways we can use k-nearest neighbors, which is another machine learning algorithm, to create these type of graphs. So, but once you're given the graph, you can then define algorithms that apply clustering on the graph itself. So you lose the data space, and you now live in this graph. And so, points that are connected, right, there will be points that are closer to each other. So if I use some type of cutting algorithms on the graph, right, then I can just cut pieces of the graphs, and those are my clusters. Again, here I need to define the number k of clusters as well. So here is some of the elements that are associated to these graphs. You create an agency matrix, which you have a matrix which is the size of your data space. 1 if the 2 points are connected, 0 otherwise. You have a degree matrix, and you have, this is called appellation, and it's the And so you then use this matrix here, and you apply clustering on this matrix, and that's how you define the spectral clustering. Extremely nice theory behind, again, for if anyone is interested, there are some really nice papers on this as well. So again, I gave you these 3 different methodologies, kind of the intuition behind what they are. And so now, we compare. So we noticed that all 3 techniques identify the same features in terms of the features that drove the clustering. Not every feature, not every variable in your data set will be useful for the clustering, right? There will be features that are more important, that define the differences across the different clusters. Income, housing units, nothing surprising here, unfortunately. Income, housing units, the age of the housing units, economic hardship indicators is still, you know, these are indicators. There's a lot of segregated areas in Chicago. So spectral clustering provided the strongest results, but compared to k-metoids, it was kind of similar. So we actually ended up using k-metoids for the deliverable to our partner. And then the self-organizing maps were not that helpful. So here is kind of like find the difference. So these are the results displayed on the map. So these are this entire region, and I will go through the details of the clusters in a minute. So this is kind of gives you an idea of the differences, right? It's kind of like that crossword game or something that is just trying to find the differences. So let's see if you guys know. So this is Chicago. This is Cook County, but a little bigger, right? So this is the urban area. Remember when I told you that? So these little squares, these little, it's not even squares, whatever these little areas, units, those are the tracks. Yeah, this is our data level. So as you can see, this is in the city, so the tracks are small because you have a lot of people in the city, right? But as you move out to the suburbs, this is one track. This is out in a very, you know, like a place with very few people. This is Kendall, I think. So all the different colors represents the different typologies. Remember, we defined 8 groups, right? Each color defines a different group, and I will go through the groups in a minute. So we ended up using this result. The brown area is about similar between the two. The blue is also similar. The pink is similar. We noticed major differences in the city. So k-metoids and spectral clustering did not agree. In the city, there were quite a few that were placed in the same categories, on the same typology, but not all of them. In fact, the yellow typology in the spectral clustering is different from the yellow typology in the k-metoid. Okay? So let me explain what these different typologies or type are. So here is the result. The maps are different because this is done by different tool. So well, let's see. We have 1 and 2, our most distressed areas. They are in urban communities. They are in the west and south side of Chicago. We also noticed some of them in other larger communities in Illinois. I have 7 minutes left. And so then we have, you can notice like this bullseye ring. So we have, this is the Gold Coast. This is high income, younger, no kids, small households. Here again, you have distressed, low income, low education attainment. The green is different from the yellow for a couple of things. The income is higher, slightly higher, and the households are bigger. So those are primarily households with, so again, we're talking in percentage-wise, right? But relatively speaking, they have a higher number of large households, 5 to 6 more people. So those would be, again, larger families. What else? The 4 is this older stock of housing. If you are from around Chicago, you know what I'm talking about. This will be Berwyn. So this will be suburban Cook County. And then these purple 5, those are the high-income, wealthy neighborhoods, high education attainment, high home value, no distress, family, children, that kind of stuff. And then we have the 6 is, 5 is the moderate income. So I'm getting confused with the colors. And the 6 is the highest income. So that's the orange part. So here will be Highland Park, what else over there? Winnetka. Here we have Hinsdale, we got Northbrook, Glenview, kind of high income communities. And then the interesting part is this, number 7, this is the growth cluster. This is where you have a growth in the population, growth in the number of houses, newer homes, and you notice that they are out in the suburbs, but more interested, it's right here in the loop. So it discovered this tiny little, the high development area in the loop as well. And then the 8 is the middle income, suburban, slightly aging, but families and children. So, So I'm going to skip this because this is just a detail of what I just said. So again, you guys can look at it more in detail. And let me show you the visual analytics tool, because the problem we had was we had a problem of how do you give this information to people. I mean, now you have this government agency, or sorry, this local organization, and they're supposed to use this, right? I mean, there's a lot of data behind this, like features and features. So we had different ways. So we decided to do this, and maybe someone might have a better idea. So one is to create this table here, which is like, what is that? So this, oh, sorry. What happened?
Escape.
Escape. Skip doesn't do anything.
And you gotta help.
You don't help me. So this table, we thought, okay, let's use this table, which is, so within each, so this is a coloring map of the variables, and we thought, okay, so this might be, so we have the quartiles, which kind of gave an idea. So here would be the stress and income, and this is the hardship. So kind of give an idea about numbers and give them something that they could use. And then the other thing we did was creating this visualization here. So this is a tool that is, it's work in progress, so it's very buggy. The values there, don't look at the values because some of them don't make any sense. But the idea is, this is built by one of our graduate students and is using D3. So we want to create this interactive visualization where you have the variables here. And so we can click on any track, and you get a histogram, and then the red line here represents the value for that specific track. So again, work in progress. We're going to add more features, because for instance, we can't click on multiple tracks just yet. So here it gives you a sense of what we're trying to do, how to make this data available and usable to non-statisticians, to non-computer scientists. And so we also want to add additional features, which is so one of the things that we realize that we want to learn about is that if you look at the map, right? So this is the map. So the interesting part of this map is that we did not use longitude or latitude in this clustering. However, the clustering follows some geographical order. If you look at the map here, the tracks belong to the tracks are, so the colors are not all over the place, right? You see parts of the map that have specific colors. So, and the question would be, so what happened to those clusters, like clusters that, oh, those tracks that are neighboring, right, between different types? Do they belong, so because I would expect those tracks to have a different, you know, gradient. So like this track, so this is the, this track here, right? So, okay, so it's colored pink, but is it going to be similar to the yellow? The yellow is a completely different type. The yellow is so one is high income, the other one is low income, right? Is it possible that I cross the street and I get in a completely different neighborhood? Yeah, sometimes you can, and it's true you can, but often you don't, right? So often the difference is not so strong, right? So the idea would be to analyze these tracks that are neighboring between two different types and evaluate whether their characteristics maybe are more of a kind of a merge, a morphing into the other typology as well. So these are all ideas that we want to investigate. Obviously improve the interactive map where and the other idea will be to also use this map to gain and to interact with the people that understand the neighborhood. And so related to my point, let's say someone says, okay, you know, this is pink, but really I know that area. It should be yellow, right, in terms of the type. And so the idea would be to have a map where I can input that knowledge and change the clustering membership of that specific track to make it interactive, where it's not just visualizing the data, it's interacting with the data and providing that domain knowledge that is so important in data science. So that is the end of my presentation, and I have questions too. So, you guys have any questions?
So let's thank our speaker. We've got about 10 or 15 minutes for questions, so please ask away, guys. Right now.
Yes.
When you're mapping higher dimensional data subsets, like when you have 60 attributes and you're mapping it into like a two-dimensional space, do you weight the different attributes? So like when you, is the weighting done automatically? Is there any weighting done at all, or is it sort of determined automatically by the algorithm? Okay,
so the map that I showed you, let me give you the map. That is not the projection. That is just here I'm just mapping the typology.
Well, I was more talking about that when you were discussing like, you know,
the self-organizing maps?
Yes.
For the self-organizing maps, okay, so with the self-organizing maps, you define this topological map, and the way they're, so each node or neuron in that map is defined by a set of weights, and the weights measure the similarity with the point. So to answer your question, whether the features that are more important in defining similarity between points will have a stronger weight in creating that topological map.
So that weight's determined automatically by
the weight is determined by the algorithm. See, so it's learned from the data. So there is a function that measures distance, and also the function depends also on the boundaries around. So it's a really, really interesting technique. You should look into it. Yeah, there are a lot of different parameters that go into that. Yes?
Do you have the ability, or do you envision the ability to do time step comparisons with, say, multiple experiences with a census? So if you have, say, a yellow track next to a purple track, is it more likely for the yellow to become purple or the purple to become
good question.
yellow? The dynamics of...
Yeah, that's a really good question. We did a similar study. So this is version 2 of the study. We did a similar study in 2010, but just for Cook County. And for that, we used 1980, 1990, 2000, and 2010 census data, and we looked at the transitions, and we tried to do a little bit of that work. But I don't know, sometimes, I think with census data, I don't know if you get enough sensitivity or something. But yeah, we tried to do that. So at the core, at the kind of a high level, we were able to do that, yeah. Okay. You guys recognize your area? We was from Chicago. Did you find yourself in that map? Where do you live? Where are you from?
Right outside Chicago.
Oh, there you go. What about you?
I'm from McHenry County, so I'm a little bit farther away.
Oh, farther away.
Not too far.
Thank
All right,
you.
let's thank our speaker one more time.